Temperature coefficient of resistance is the resistance change factor per degree Celsius of temperature change, or call it the fractional change in resistance at 0 degrees Celsius for every degree Celsius rise in temperature. Now, temperature coefficient of resistance is represented by the alpha sign, and it's written like that. Now, this is a graph that is representing resistance against temperature, and looking at this graph, we're having a positive slope. Now, this positive slope shows that when the temperature of whatever the conductor is increases, the resistance also increases. This is according to the graph. Now, how does it happen that the resistance of a certain conductor will increase with increase in temperature? Now, when the temperature of a conductor is increasing, or when it is increased, the heat that is causing this temperature increase is picked up by the atoms in a metal conductor. And as a result, the atoms within the conductor increase in their vibrational energy, or call it the kinetic energy. So these increased vibrations due to the increase in kinetic energy make the electrons flowing through the conductor to be more likely to collide with the atoms. Because the electrons are now experiencing more collisions as they flow along, this therefore means that they are experiencing a higher resistance, and this higher resistance is because the metal's temperature has been increased. When a conductor is such that an increase in temperature causes an increase in resistance, then that kind of conductor is referred to as a conductor that is having a positive temperature coefficient of resistance. In other words, conductors that are having positive temperature coefficients of resistance are those ones whereby their resistance will increase with increase in temperature, and as such, the resistance against temperature graph will always give you a positive slope. These kinds of metals, we have nichrome, we have tungsten, and others. However, there are metals like germanium and silicon that have their resistances decreasing with increase in temperature. So when we're looking at it in this context, if it's to plot a graph of such, it would mean that as you're increasing the temperature here, this resistance drops, and as a result, you'll find that the graph will always have a negative slope. Again, such metals whose resistance has decreased with increase in temperature are said to have a negative temperature coefficient of resistance. Now, looking here, the temperature coefficient of resistance from our definition, we said that it is the resistance change factor per degree Celsius rise of temperature change. And looking at it, it's represented by the alpha sign. This alpha sign is therefore going to be equal to the increase in resistance per unit temperature rise, like we had stated it in our definition, at degree Celsius, per degree Celsius rise in temperature. So it's increase in resistance per unit temperature rise, divide that by resistance at 0 degrees Celsius. Now, the increase in resistance per unit temperature rise, if you look at this statement, it is more like it is the slope. The slope of this graph. If you're to see the increase here in temperature per unit degree temperature rise. So how much resistance is increasing per unit? So how much resistance is increasing is the new resistance minus the original resistance. Let's say the temperature increased, the resistance increases to r theta from resistance at 0, or from this is the initial. So the change in resistance is r theta minus r naught. So according to the definition, it is the increase in resistance per unit increase in temperature. So when this increased from here to here, what was the corresponding change in temperature? It is this theta minus that. This is the change in temperature. So it is theta minus 0. So this is the statement here, that the increase in resistance per, or divide that by the unit temperature rise, divide that by the resistance at 0 degrees Celsius, and this is how we come up with this, that it is r theta minus r naught over theta minus naught. You realize this is more like the slope of our graph. Divide that by the resistance at 0 degrees Celsius. The resistance at 0 degrees Celsius is the resistance when the temperature is 0. It is right here, denoted by r naught. So from here we go ahead and go on with the arithmetic. So it becomes alpha is going to be r theta minus r naught. Divide that by, when we divided the resistance at 0 degrees Celsius, this is the expression we came up with. When we reorganize this expression in such a way that it is flat, we multiply times r theta naught times r theta naught on both sides, so that this goes with that. This side you remain with r theta minus r naught is going to be equal to alpha, which is that, times r theta naught, the one you multiplied on both sides. And then you rearrange this equation to make r theta the subject of the formula. You find that resistance at a temperature theta is going to be equal to resistance at 0 degrees Celsius into 1 plus alpha theta. So now this is the expression that we shall be using in our calculations and other expressions also when we're trying to calculate for the temperature coefficient of resistance, which is denoted by that alpha sign. Now if I may connect this expression to our graph. If you look at our graph, we saw here that our slope, this slope, is going to be the change in y. Of course, the change in y is r theta minus r naught. R theta minus r naught. Divide that by the change in x. The change in x is theta minus 0, which is theta minus 0. Of course, this is going to become r theta minus r naught over theta minus 0 is theta. This is going to give us the slope. And if we are to make this a flat equation, we multiply theta on both sides, you'll find that this will end up being s is going to be s theta is going to be equal to r theta minus r naught. And when we make r theta the subject of the formula, it means that r theta is going to be equal to r naught, because this r naught comes this side. So r theta, which remains, is equal to r naught plus s theta. Now I want us to relate this to this. Actually, let's take it to this part of the equation. If you're to relate this expression to that, let me write it right here. This is r theta. If you're to relate the two, you see this is r theta is there. R theta is going to be equal to r naught. So r naught is right there, plus alpha r theta theta, r naught theta. So you find that here we're having a theta and we're having a theta there. So it means that this slope is equivalent to that. So it means that when you're plotting a graph of resistance against temperature, the slope you get here is actually equivalent to alpha times r theta is equal to alpha times alpha times r naught, where r naught is the resistance at 0 degrees Celsius and alpha is the temperature coefficient of resistance. So should you draw a graph of resistance against temperature and you've been given a certain table of values and then you draw your graph, the slope of that graph, you just equate it to alpha times r naught, where when you make alpha the subject of the formula, you end up with the slope you will have required over r naught, and you're able to get your temperature coefficient of resistance using the graph. Well, another way to look at this is, if you analyze this thing, it's actually in the form of a straight line. We know that the general form of an equation of a straight line is given by y is equal to mx plus c, where m is the gradient and c is the y-intercept. Now, if you look at this equation and relate it to that one, for example, you'll find that the value of y is actually r theta. This is the value of y. The value of x is where the gradient is m. So if you look here, this is the slope we identified, so it means the value of x is right there. And the y-intercept is actually r naught, which is c. And if you look at this thing, if we were to plot a graph of y against x, you realize that our value of y is corresponding to r theta. Our value of x is the theta, the temperature, theta degrees. Then our y-intercept, the part where the y-intercept is crossed, is actually r naught, which is that one. This is our value of c. And so it means that this constant here, alpha r naught, is actually our gradient. So in form, you could also look at it that way. What I'm trying to raise here is that when you are trying to find the temperature coefficient of resistance of a metal, when you're using a graphical method, that is, you've undergone some tests and you have drawn a table of results, a table like this, that is giving you the resistance and then the temperature, and then you have some values. When you plot that graph, you're simply going to get the temperature coefficient of resistance by equating it to the slope you will have gotten. Divide that by the resistance of at 0 degrees Celsius. So a coil of wire has a resistance of 30 ohms at 20. So the resistance at 20 degrees is 30 ohms. And that resistance at 60. So the resistance at 60 is 34.5 ohms. They want you to calculate the temperature coefficient of resistance. Now, from the expression we've just looked at previously, we know that resistance at an unknown temperature theta is going to be equal to resistance at 0 degrees Celsius into 1 plus alpha theta. So what's the resistance at 20? We are going to use this to substitute this to come up with two equations that we are going to solve simultaneously. So now the resistance at 20, we know that the resistance at 20 is 30. So the resistance at 20 degrees is 30 ohms. Is going to be equal to the resistance at 0 degrees Celsius, which we don't know, into 1 plus alpha times theta. Now the value of theta in this case is 20 degrees Celsius. So it means that it's going to be plus 20 alpha. This is 30 ohms. 30 ohms is the resistance at 20 degrees Celsius. That's right, huh? So we go ahead and find for this, substituting this expression, we know that the resistance at 60 degrees Celsius is 34.5 ohms. So we still know that 34.5 ohms, which is the resistance at the theta, which theta in this case is 60, is going to be equal to the resistance at the unknown temperature, the resistance at 0 degrees Celsius into 1 plus alpha theta. Now our value of theta in this case is 60, so it is plus 60 theta times alpha. Now here we are interested in finding, this is our equation 1, this is our second equation, and here we are interested in finding the value of alpha in, so we are going to solve those two simultaneously. Now the easy way out here is to simply divide the two equations. So in simple terms, we are going to say equation 1, divide that by equation 2. So that when we divide the two, the r naughts cancel out, and when those r theta r naught cancels out, or the resistance at 0 degrees Celsius, when they cancel out, we are able to isolate alpha, and we are able to get the temperature coefficient of resistance. So in this case, we are going to, equation 1 is that, so it's going to be 30 is going to be equal to r naught into 1 plus 20 alpha. Divide that by equation 2, which is that one, divide that by 34.5, divide that by this other side of the equation, which is r naught into 1 plus 60 alpha. So of course this r naught and that r naught cancel out. We cross multiply, that becomes 30 into 1 plus 60 alpha is going to be equal to 34.5 into this times that is into 1 plus 20 alpha. So when we open brackets, it becomes 30 plus 1800 alpha is going to be equal to this times that is 34.5 plus this times that is going to give us in this question, we are being told that the resistivity of mild steel is 5 times 10 to the power negative 8 ohm meters at 20 degrees Celsius, and its temperature coefficient of resistance is that. Calculate the resistivity at 60 degrees Celsius. Now, if I may summarize this question, we are being told that the resistivity of mild steel, so the resistivity of mild steel at 20. The resistivity at 20 is 15 times 10 to the power negative 8 ohm meters. That's the resistivity at 20 degrees Celsius. And we're also being told that its temperature coefficient of resistance is 50 times 10 to the power negative 4 per Kelvin. So they want us to find the resistivity at 60 degrees Celsius. Now we all know that the resistivity, the formula for resistivity is the resistance at that unknown whatever temperature times the cross-sectional area, divide that by L. But now if you look at this question, we've not been given anything like area, we've not been given anything like length of the conductor. So let's formulate our equations. When the resistance is 20 degrees Celsius, what is our resistance at 20? So we know that the resistance at 20 is going to be equal to resistance at 0 degrees Celsius, which we do not know, into 1 plus alpha times 20. Now it is 1 plus our alpha here. We know our alpha right here to be the temperature coefficient of resistance is already given as 50. So let's first, it's going to be 50 times 10 to the power negative 4, multiply that by the theta, which is 20, like that. So that will make like our first equation. Then also we have our second equation. They want when the thing is at 60 degrees. So the resistance when it is at 60 is going to be equal to the resistance at 0 degrees Celsius into 1 plus alpha theta. Now our value of alpha is still the same, which is 50 times 10 to the power negative 4, multiply that by theta, which is 60. That's our equation 2. So if we are to divide these two equations, we shall say that equation 1, divide that by equation 2, we'll end up with equation 1, which is resistance at 20, divide that by resistance at 60, is going to be equal to resistance into 1 plus 50 times 10 to the power negative 4 times 20, divide that by R naught into 1 plus 50 times 10 to the power negative 4 times 60. So of course this will cancel with that. R20 over R60 is going to leave us with 1.1, divide that by 1.3. So we have an expression there. Let's give it a star. We have an expression, so we will go ahead and find another expression, and we shall be using that expression using our formulas for resistivity. So this is our first expression. Let's go ahead and find the expression using resistivity. We know that resistivity is going to give us resistance times area over the length of the conductor. So in this case we have the resistivity of 60. The resistivity of 60 is going to be the resistance at 60 degrees times the area of the mild steel divided by that by the length. That is our equation 3. Then we also have the resistivity at 20 degrees Celsius. The resistivity at 20 degrees Celsius is going to be the resistance at 20 times the area over the length. That is our equation 4. So again, we shall say Roman 3 divided by Roman 4, equation 3, divide that by equation 4 to get another expression. So the resistivity at 60, divide that by the resistivity at 20 is going to be giving you the this, which is resistance at 60 times area over L, divide that by the resistance at 20 times area over L. Now of course this area and this L, they will cancel out. Since it's mild steel, they have the same area and the same length. So from here we shall end up with the resistivity at 60, divide that by the resistivity of 20. Now this resistivity at 20 is given by that, which is 15 times 10 to the power negative 8, is going to be equal to the resistance at 60, divide that by the resistance at 20. So now the question, remember, wants us to calculate the resistivity at 60 degrees Celsius. And right here we're having an expression that is having the resistivity at 60 degrees Celsius. But do we have the resistance at 60 and the resistance at 20? We can get that from our earlier expression. Our earlier expression here tells us that the resistance at 20 is 1.1 over 1.3 times R60. So if we make R20 the subject of the formula here, it becomes resistance at 20 is going to give us 1.1, divide that by 1.3 times resistance at 60. So if you come and substitute for this right here, this is going to become resistance at 60, divide that by resistance at 20, you substitute that, which is 1.1, divide that 1.3 times the resistance at 60. So that this cancels with that, you remain here with 1, divide by this expression, divide by 1.1 over 1.3, which is the same as saying 1 times 1.3 over 1.1, and you will end up with your answer.